So given a vector A and a vector B, we can say that the resultant vector is the vector A plus B. So the effect of adding a vector to another vector results in a vector that is the sum of the two vectors. Easy enough. Well, there also happens to be a vector that is completely opposite or exactly opposite, such that if I add the opposite vector to the resultant vector, I end up with the number 0 or the 0 vector. And this is called the equilibrant vector. So the equilibrant vector has the value of opposite A plus B. So the equilibrant vector is the vector that gives us the value of 0 when combined with the resultant. In the same way that 2 combined by addition to -2, the opposite of 2, so 2 plus its opposite equals 0, vector A plus B plus its opposite equals 0, and the opposite of vector A plus B is the equilibrant vector. That's really all the information there is on that. That's probably why I said it 49 times. Felt like there wasn't a lot to say, but there's a lot to do when we work problems involving the resultant. Involving the equilibrant. So let's do an example that sort of puts the information together for us in a meaningful way. Say we have some vector A, and the vector A has a magnitude of 15 miles per hour and a bearing of 125 degrees. And vector B has a magnitude of 12 miles per hour and a bearing 0.45 degrees. And we want to find the equilibrant vector for this set of vectors. So let's put this together. Well, we're talking about 15 miles per hour at a bearing of 125. And 12 miles per hour at a bearing of 0.45, which just means 45 degrees from north in the clockwise position. And 125. So we want to know, first we have to figure out what is the resultant vector. And from that point, we'll figure out what is the equilibrant vector. So let's redraw this so that we can map the most important information. So in this case, I have a vector with a magnitude of 15. And I add to that a vector at 45 degrees, the magnitude of 45, whoops, I didn't label that, sorry, 45 degrees, 12. So this is a magnitude of 12. And so the resultant vector in this case is this vector right here. And we want to know what this vector is. So far, the only angle value I know is this angle value here, because this can be calculated 125 minus 45, and that's just 80. So if I know that this angle is 80, that's very useful, because if I were to transpose or duplicate this first vector here in this position, if I know that this is 80 degrees, then I know that the opposite interior is also 80 degrees. And so I know that this angle, which is really in our other diagram, this angle is equal to 100. So I can label this 100. And now that I have two sides and an angle, I can use the law of cosines to find the magnitude of C. Whoops, I erased it. So C squared equals, well, one side equals each of the sum of the other two sides squared, so 15 squared plus 12 squared minus 2 times the product of the other two sides, 15 times 12, times the cosine of 100 degrees. I'm going to open up my calculator, and there's no sense in making you watch me punch buttons. I've just put in the exact expression, and I get a value of 431.513. So that equals c squared. So c equals the square root of that value, which is 20.7729. I'm going to just round it to 20.77. So now I can use the law of sines to find this angle. So let's say that the sine of, let's call it alpha over 12, so the alpha over 12 has to be equal to the sine of 100 over c, but c is 20.77. So I'm going to multiply both sides by 12 and pull up my calculator again, and I've already entered the value. You can see that it is I can't see it, it's so small, 0.65689. But remember, this isn't the value of the angle alpha, this is the value of sine alpha. So alpha then equals the arcsine of 0.5689. So the value of alpha is the arcsine of this value, and that is 34.679 or 34.68. So the magnitude and the angle, well, this inside angle is 34.68, but I really want to know what theta is. So theta equals 125 taken from here where I started minus 34.68, which equals 90.32. And now what I need to know or want to know is what would the equilibrant be? What would have to be the angle for the equilibrant? And I really only need to know the angle because I want to know what angle is exactly backward or in exactly the opposite direction from my resultant, but has a magnitude of 20.77. That part I already have. So, well, I'm looking for this angle. And this angle is totally easy to find because it is exactly this angle, 90.32, plus 180. So I already have 90.32. If I add 180, I get 270.32. Therefore, the equilibrant vector has a magnitude of 20.77 miles per hour at a bearing of 270, turned off, 0.32.